All right. We are going to talk a little more about gradients today. The gradient is one of, like I said on Friday, the gradient's one of our kind of big, important ideas for the rest of the semester. So let's review our important ideas from Friday. The directional derivative in the direction of some vector of our function is the rate of change of the function in the direction of the vector. In our vector, we want our vector to be a unit vector. Our gradient, del f, is df dxi plus df dyj plus df dzk. And if we just had two variables, we just have I and j here. And we defined our del operator as ddxi plus ddyj plus ddz. Okay. And del has to operate on a function or another vector in order to have any meaning. It doesn't have any meaning on its own. It has to operate on a function. And in chapter 15, we'll do operations with del on other vectors to get some different results. The directional derivative in terms of del of our function is just del f dot u. And finally, at the end of what we talked about on Friday, we said that del f points in the direction of the maximum directional derivative. So these are some of the important ideas about the directional derivative and about the gradient. And I mentioned that sometimes you'll see del f written as the gradient of f. Just so you recognize both forms. And a reminder, because this is going to come up here and there in this chapter, that if we have a vector xi plus yj, vector that is normal to this vector is minus y I plus x j, or yi minus x j. So to find a vector that's normal to a vector in the plane, we switch the x and the y and change the sign on 1. That will come up a little bit here and there as we move on. So let's look at another important property of the gradient. If we have a coordinate system, this is our coordinate system in the xy plane. So we're just going to draw a section of the xy plane. And we're going to look at a level curve. So in red, we're going to say this is a portion of the level curve of z equals f of xy. And on our level curve, what's the important property of level curves relative to the function? How do we find level curves of a function? It's a constant. So f of xy is constant on the level curve. Now here's our normal, let's draw a normal vector, or a tangent vector, to the level curve. There's a tangent vector, and we're going to say this is a unit tangent vector. So u is tangent to the level curve. And the length of u is 1. So u is our unit tangent vector. On the level curve, if we want the directional derivative in the direction of u, what is our directional derivative going to be? In this direction. What's our function? Constant? The derivative of a constant is 0. So because we're on the level curve, the directional derivative is going to be 0 because z is constant, f is constant. So that tells us that del f dot u is 0. Del f dot u is the same as a directional derivative in the direction of u. If the dot product of these two vectors is 0, what's the angle between them? 90 degrees. Since the dot product is 0, del f and u are orthogonal. So this tells us, this is our another important property of the gradient. The gradient is orthogonal to the level curves of f. So that's our next important result. So we have if f is differentiable, at some point, and our gradient at that point does not equal 0, because if the gradient is 0, our directional derivative is 0 everywhere. If the gradient is not 0, then del f at x0, y0 is normal to the level curves at our point. So our gradient points in the direction of the maximum rate of change of f. This tells us that the maximum rate of change of f is at a 90-degree angle to the level curves. So just kind of as we would intuitively expect, if we're looking at like a topographical map, the direction, the direction that you can climb in the steepest is perpendicular to your lines that indicate your altitude. That's going to be going in the steepest direction if you go perpendicular to those lines. So kind of like we would expect. Now this idea is going to be very important when we start working with level surfaces, when we have a function of 3 variables, because our gradient is going to give us a vector that is normal to our surface. And normal vectors are going to be very important as we move on. Questions before we do some examples? All right, so if I asked you to discuss the importance of the gradient, we'd be able to do that now, right? All right. So let's look at, let's say we have f of xy equals x times y. We want to find a normal vector to f of xy equals -3. So what this is, we're looking at the level curve of this function, and our constant is -3. We have xy equals -3, so we're wanting to find a normal vector to this level curve, and we want it at the point -1, 3. So we remember that our gradient, del f, is normal to level curves. So del f in this case is going to be yi plus xj. And at -1, 3, del f is going to be 3i minus j, and that is our normal vector. So at the point 1, 3, this vector is normal to xy equals -3. That's it.
So it doesn't really matter then what it's equal to?
No, as long as it's a constant. As long as it's a constant. So yeah, the gradient gives us the normal vector to the level curve, so our function has to be a constant. Any other questions? Let's look at one more example, and then we'll get to the fun example. These are just the computation examples, the plug and chug examples. This time we want to find a unit normal vector. To 3x squared minus 2y squared equals 1 at 1, 1. In the plane, if we're just looking at this in the plane, what kind of graph is this? Hyperbola, right? We have opposite signs here. So our graph is a hyperbola. So this gives us a tool. If we wanted to find a normal vector at a point to any kind of graph in the xy plane, this would be a way that we could do it. So this is the level curve of f of xy equals 3x squared minus 2y squared at our constant equals 1. We could think of this as the level curve of this surface when our constant equals 1. The level curve of our surface is hyperbola, or hyperbolas. So we remember that del f gives a normal vector. So we calculate our gradient. Del f is 6xy minus 4yj. And at 1, 1, we have del f equals 6i minus 4j. this vector is normal to our curve here, but we want a unit vector. So the length of del f, we're going to divide by the length, is the square root of 36 plus 16. So this is the square root of 42. So our unit vector equals del f over the length of del f, which is 1 over square root of 42 over 42 times 6i minus 4j.
Do we have to rationalize the square root?
I don't care.
of
36 plus 16 whole 42.
52. Thank you. And this is one thing that I do like to argue, Andrew. I argue that arithmetic and mathematics are two different things. They're related, but they're different. So I tend to be kind of bad at arithmetic, but okay at mathematics. Arithmetic is real math. I argue with my wife about it frequently, but I also argue that words rhyme with themselves, and she says they don't.
That's
What?
the whole interest degree.
What's the point?
To not rhyme a word with itself.
What?
I argue with my wife that arithmetic and mathematics are different. She says they're the same thing. I say they're related, but they're different. But her father was a English professor, so I always tell her that words rhyme with themselves, and she says they don't.
Like it's like saying cat and cat rhyme.
Right. So she says they don't rhyme, and I say they do.
Why would a word rhyme with itself?
What-
What's the point of that?
What's the definition of rhyme?
Sounds the same at the end.
But
Sounds the same at the end, right?
it's a rhetoric tool. Language is like, rhyme is not really, that's why you can't discuss.
All right, any other questions except for, other than my poor arithmetic? No, okay. All right, let's get to this good example. I love this kind of problem. This is a really fun, really good problem. All right, so we have t of xy equals t. Yes, that's a t. T of xy is 100 minus x squared minus 2y squared. And this is the temperature field.
Wait, is this your favorite one?
This is my favorite example from this whole section.
That sounds like the last.
The temperature field at any point on a metal plate.
What kind of a metal plate are we talking about?
Like an example of a temperature field on a metal plate could be a griddle. Like the top of your,
Well, I didn't know if we're talking like, I don't know, a metal piece
it doesn't matter, just some piece of metal.
of got it.
And this models the temperature at any point on that chunk of metal.
Okay. Okay.
We want to find, this is where it gets fun, find the path of a heat-seeking particle placed at the point 43. So we'll leave aside the question of what exactly a heat-seeking particle is at this point, because it's not important. All that's important is the math that we're going to do here. We want to find an equation for the path of this particle. So let's get an idea of what we're talking about here. If we were to look at, let's draw a. Here's my XY plane. If we wanted to draw the level curves of this function, what would they be? It's an ellipse, and the major axis is x or y? Y, x. If we set this equal to a constant, the major axis is going to be in the x direction. Because we want, for our ellipse, we want it equal to 1, so we're going to divide by something, so that we're going to be dividing by the biggest number under x. So if I draw, I'm just going to sketch some level curves. I don't know exactly what they look like, but they're going to be ellipses. So our temperature field on this plate looks something like this. And we're putting a particle over here at 4, 3. So we're going to start a particle, say right here. Say that's 4, 3. It's going to move in the direction of the maximum temperature difference. So it's going to go here, then it's going to go here, and wherever it ends up in our level curves, and it's going to go here. And we want to find an equation for that path. Because every time it's going to start at this point, it's going to move in the maximum, in the direction of the maximum temperature. But as soon as it moves, that direction changes. So its path change is continually changing as it goes along this metal plate. And we want to find an equation of that path. So how does anybody have an idea of how we want to start with this? The gradient is a normal vector, and the gradient also points in what direction? The maximum rate of increase of temperature, or the maximum rate of change of the temperature. So our gradient is going to be the tool that we're going to use here. One of them, anyway. Del T So our gradient points in the direction of the maximum temperature change. So let's calculate our gradient. Del T is going to be what? Minus 2x I minus 4 yj. Now we want to find the path. So our path, we're going to want some kind of expression for the path of our particle. So our path is going to be our position vector, r of t. Is some function of x I plus some function of y as a function of t, j. That's our path. Anybody see where we can go with the path? R prime of t is x prime of t I plus y prime of t j. What direction does r prime point relative to our path? Tangent to our path. So if our path is in the direction of the maximum rate of change of the temperature, how is this r prime going to be related to our gradient? Orthogonal?
Yeah, dot products and zero.
So if this is pointing in the direction of the maximum rate of change of temperature, and our tangent vector to our position is going to be in the direction of the maximum rate of change of temperature. How are these two related? They're parallel, so they differ by a constant. So that gives us our equation that we can work with. These both are going to point in the same direction. So del T, I'm going to say R prime of T is some constant times del T. They're going to be scalar multiples of each other. And this will give us our equation so we can find our path. So we're just going to write these expressions for these two out and equate components. So x prime I plus y prime j equals c times minus 2x I minus 4yj. This tells us that dx dt equals some constant minus 2cx, and dy dt equals minus 4c 4cy. So I'm just equating components here. Anybody see where we need to go from here? Well, we have dx dt and cx. We want to get x and y, x in terms of y in terms of x somehow. I'm going to solve each of these for dt. So I'm going to say that dt from this equation, dt equals minus 1/2, and I'm just going to call this other constant c1 dx over x. And here dt is minus 1/4 some other constant. Let's see, I'm dividing by the constant, so I'm just going to call that 1 over the constant, because I need to divide both sides. dy over y. And now I can equate these two. When I equate these two, I get 2 dx over x equals dy over y. And we know how to solve this, right? How do we solve this one? Can we just take the integral of both sides? We're going to integrate both sides. So we get 2 natural log x equals natural log y plus some other constant. Change this to exponential form. So I get x squared equals c3 y. So I'm put these two in exponential form. And 2 natural log x is natural log of x squared. So that's where my x squared. And I get e to the natural log y plus, and then just get another constant there. Okay? And we know from our initial condition, we know that our particle starts at 4,3. So plugging in 4,3 here, I get 16 equals C3 times 3. So C3 is 16/3. And I can say that y equals 3/16 x squared. And that would be the path of that heat-seeking particle on that plate in this temperature field. And the crux of the problem was that we recognized that the gradient and the velocity vector pointed in the same direction, so we could equate them. I really like this kind of problem.
Why do you like it so much?
It's just a fun problem.
Is
It
it
brings together several things that we've talked about. We've talked about the gradient and the fact that it points in the direction of maximum rate of change of our function. It brings in position vector and velocity vector. And we know that that's tangent to our path, so it mixes together lots of different things that we've talked about. And I also think it's fun just to think about what a heat-seeking particle would be. Any questions on that? All right. Homework. All right, there you go.